All right, recording is rolling. Yesterday we started a new topic, momentum and momentum conservation, and I got about halfway through the story I wanted to tell you guys, so we'll do the other half today. Okay. Oh, yesterday I did pick up your guys' quizzes. I'm still waiting for a few more of those to come in, but if you turned in yours yesterday, then I did grade it, and I got your grade on focus. Overall, you guys are doing really awesome on that energy quiz, so yeah, way to go there. Okay. Also, I made some posters that I posted to Google Classroom over the weekend. I just got those hung up today. So let's look at these because again, we're about halfway through this momentum story. So yesterday you guys saw this conservation of momentum. Okay? So if you had to follow the momentum bits, which is just mass times velocity. So before a collision and after a collision, they have to equate. Okay? Yeah, and that's what conservation of momentum is really good at solving is collision type problems. Okay? I'll remind you guys why too. I'll flash through yesterday's notes. Right? Then there are special kinds of collisions. So, I mean, you can have lots of different kinds of collisions, right? Like, what exactly is colliding? Right? Is it like two bouncy balls, or like these Newton's cradle balls that can be really bouncy? Is it like two half-deflated tennis balls, or is it like two balls of clay? Well, the page you guys are looking at right now is like two balls of clay that collide and stick together. This is sort of like a boundary condition on collisions that you can have. And hey, this looks like a modified version of the general expression of conservation of momentum, right? Out of all the momentum bits, and these two are going to collide, make one giant mass, and zoom off into the sunset together. And that's how they go. AP tends to ask questions about this more than the next slide you're going to see with elastic, because math is pretty straightforward, right? Yes, yeah. Okay. Now the next one, now this we haven't got to in the notes yet. This is going to be today's notes. Is the other extreme you can have, like perfectly bouncy, like those Newton's cradle balls that you guys just saw. Right? And how that works out is that not only is momentum conserved, now this is like a law of the universe, right? So, okay, momentum is conserved, okay, so no surprise there. But also, kinetic energy happens to be conserved, right? So when I flash up the notes from yesterday, we'll take a look at what's happening to kinetic energy with those other kinds of collisions, which you guys saw yesterday. I'm just going to remind you guys. Okay? But if it happens to also be conserved, then you have this system of equations. Here's the solution to that system. And so later on the notes today, I'll handwrite this out and I'll talk a little bit more about that. But ooh, that looks like a pretty fun deal right there, doesn't it? Now AP does not give you this on their equation bank. AP does not expect you to memorize this because that looks pretty crazy going on. If AP ever asks something about elastic, every rare once in a while they do. It's usually something pretty straightforward that you can get. Like for example, I remember an AP FRQ question that just as the middle step involved two masses of the same mass. One was at rest and one collided into it, and just that happened. Okay? So, like, if you could at least fit that mental model into your head, then okay, you could move on and answer that question. And then, well, what if it's not perfectly inelastic or perfectly elastic? What if it's like two half-deflated tennis balls that like bounce off each other, but not very well? Is there some way you could quantify bounciness? That's what this is, coefficient of restitution. There's a formula for it. That'll be near the end of the notes today. And the other topic I have to talk about is impulse, which actually comes with a graph. And for that reason, I should have made that one of your posters too. So, a little oversight there. But I'll give it to you guys in the notes, and you guys can learn about all this stuff. So, impulse. Okay. All right, and that's about as far as we're going to get today. So you guys were looking at yesterday's notes, so let's do that real fast. So momentum, mass times velocity, has these units, which you can figure out by looking at the formula. Okay. Also Newton seconds, that's going to come back at the end of class today. Same unit, just alternate. Okay. Momentum is conserved before and after a collision, and that's what this is good for, collisions. We looked at a general case, so I gave you a couple masses, a couple of initial velocities, and said, what's the post-collision velocities? Now, you can't solve that by itself unless you have some additional piece of information. So I started by telling you one of the rebound velocities. Now, once I told you one of the rebound velocities, and you know everything else, then the other guy's rebound velocity is determinable. And so we got this number by plugging in all this stuff. Okay? And then we said, well, what's going on with the kinetic energy? Because what kinds of energy are involved here? What kinds of mechanical energy? Well, I don't see any potential energy. There's no height change. You just got a before and after picture, right? There's no springs, but there is energy in motion. So if you kept track of that, it actually looks like a lot of energy is missing. Wait a minute, didn't we just spend the last couple of weeks talking about how energy is conserved and how what energy is just going to disappear? Except it doesn't. Energy doesn't disappear from the universe. it just transfers into other forms that are hard for us to keep track of, things like thermal energy, like sound, like permanent deformation is a big one. Okay. Imagine if you fire a bullet into a block of wood. Do you think a lot of force times distance goes into moving those wood fibers out of the way as the bullet embeds itself? Right. Now there's an exception to kinetic energy decreasing, and that is if you have something that's perfectly bouncing, perfectly elastic. Okay? So we haven't quite got to that point yet. Okay. Right, so here is number 4. We just look at a general case again, but just sort of in reverse. What if you have a bunch of post-collision information and you want to figure out what's going on pre-collision? This is a good thought process for, let's say one day you're a forensic investigator, you see a car crash, you're trying to figure out what happened before the car crash, what led up to this, right? Might be something like that, but otherwise it's just general situation like before. Right, perfectly inelastic, collides stick together. What's the final velocity? Okay, pretty plug and chug. Again, AP tends to ask questions about this one because it's pretty straightforward, right? They combine masses and right, like that. Right. Notice that if you're doing energy accounting, it looks like all the kinetic energy could possibly go, well, in this case, maybe you have the maximum change in kinetic energy is what it should say, something like that. Like all velocities are relative. Okay. Right, then, look at this grenade exploding. And hold on, what does this have to do with collisions? Because if something explodes into 2 parts, and you film that, and you run the film in reverse, does it go and come? That would look like a collision in reverse, wouldn't it? So you can treat it that way, like sort of like inelastic, just in reverse. Right? One thing breaks into 2 parts. Right? Now, remember how 2 things colliding? It looked like we were losing kinetic energy. Right? For something exploding apart, shouldn't it seem like we're gaining kinetic energy? But that should make sense too, because there is energy added to the system from that chemical explosion. Right? Now that's as far as we got in the notes yesterday, but that is exactly going to lead into what I was about to solve next was, remember I started this whole section with an animation, right? Pitcher throws the ball towards home plate, she gets kicked back towards second base on a frictionless field. And the question was, how fast is she going back towards second base? This basically is that grenade problem, and I'll show you guys why. So, quickly. Here's. So let's get a picture of what's going on there. Okay. We got the mass of the ball being thrown at however fast that's going. So velocity of the ball. And then there's the pitcher, mass of the pitcher. Is kicked back the other way, which you guys could have said because Newton's third law of motion, right? There's some force interaction that pushes them opposite directions. Right? Velocity of the pitcher. Okay. But again, if you try to use some other method to solve for the pitcher, knowing these 3 values, if you know each of the masses and how fast you threw the ball, right? Well, you'd run into trouble because let's say like energy conservation, for example. When she's sitting there just on the mound at rest with the ball, right? How much kinetic energy is there just at rest? 0. 1/2 mv squared is 0. Then she throws the ball, and oh boy, we have kinetic energy all over the place, right? Where'd all that energy come from? Well, it came from her muscles, like the fact that she's throwing the ball. But do we really have a way to account for that with mechanical energy, with the equations from this class the last couple of weeks? Not really, right? But it's kind of like that grenade exploding. It's like all this energy just came out somewhere. Like it was stored energy. Right? But you can't do this. You can't say sum of momentum initial equals sum of momentum final. And treat this as sort of a reverse collision. Solve it that way. Okay? Now, the initial momentum in the system is the mass of the ball plus mass of the pitcher, moving at initial speed of, well, it was 0, but haven't quite got there yet. Just doing the formula version. And then once she throws the ball, then you've got mass of the ball times velocity of the ball one way, plus mass of the pitcher times velocity of the pitcher the other way. And it should add up to the original momentum, right? Makes sense? Now, you do know that the initial velocity, them just standing there at rest on the mound, had to have been 0, right? Everyone started just like standing at rest, right? So everything on the left side is just going to come out to 0 anyway, 0 kilogram meter per second. But if you want to solve this, let's make up some numbers, right? So, well, I actually do know what a baseball is pretty close to. Baseball is pretty close to 0.15 kilograms. So let's use that. 0.15 kilograms. That is, well, here's 0.1 kilograms. Here's half of that. So it's basically these two guys put together is pretty close to mass of a baseball. Or alternatively, the biggest slab weight is like 6 baseballs, pretty close to. I need to give her a mass. I'm gonna make up something. Let's say like 40 kilograms. Right, and then over here, start plugging and chugging. So mass of the baseball, 0.15 kilograms. There's one more thing you need to know. How fast did she throw it? So I'll make up something again. Let's call it 30 meters per second. Okay. Now this would be relative to, say like that, remember that buzz blimp that was going over her head? Right, that's what that number is. This is not necessarily her throwing speed, because the fact that she got kicked backwards at the same time, maybe she can throw a tiny bit faster than this, maybe like, I don't know, 31 meters per second, right? But the fact that she slides backward, you said, well, what is this number relative to? This is like relative to the ground, relative to that blimp, that buzz blimp. Her mass shows up again, 40 kg. Okay. And here's what we've been trying to figure out. Okay. How fast is she going to move back towards second base? So all this comes out to 4.5 kilogram meter per second. Right. Subtract that over. One more thing. Looks like her velocity is going to come out negative, right? I guess that's okay. Let's do that. Right. I wanted to throw a negative somewhere, but let's do it. Right. So plus 40 kg times velocity of the pitcher, and we know velocity of the pitcher is going to be negative if towards the plate's positive. Right? So velocity pitcher is 4.5 kilogram meter per second, subtracted over, all divided by her mass of 40 kilograms. And that's going to come out to 0.1125 meters per second. That's too many significant figures, but 0.11, something like that. Okay. So there you go. That's how fast she slides back for second base. Pretty slowly, but that makes sense because she had such a large mass.
On the FRQ questions, are they going to care about significant figures at all?
Yeah. AP Physics, they don't really care about significant figures. So yeah, if you're technically supposed to have like 2 and you put like 3 or 4, then yeah, they'll take that. Now, a common AP type question though would also be involving center of mass, which I haven't really mentioned, but she and the baseball start off with just like their center mass is just like on the mound just at rest, right? Okay. When she throws the baseball to the left and she moves to the right as a result, what do you think the center mass of that 2-object system? What do you think happens to that center mass? Do you think it stays just on top of the mound between these two? Yeah. The center mass just never moves. Center mass just keeps doing what it's doing. Okay. If she was already sliding and then she throws the baseball and then something crazy happens, okay, then the center mass, if you were to follow that, it would just keep moving as if like nothing ever happened. I'm looking at the center mass between her and the baseball. Okay. So the only exception to that would be if there was some kind of outside force acting on it. But if the only force interaction is between those 2 objects, then the system itself just keeps doing whatever it was doing. All right. So that is, again, sort of a reverse take on perfectly inelastic, throwing something. So let's look at the other special case you can have, which is perfectly elastic collision. Now that's the physics term for perfectly bouncy. Okay. Perfectly bouncy. I think I asked you guys yesterday when we solved the very first one of these, say for a general situation. Remember to solve this, we had to make up a rebound speed. I said, could this rebound speed be like negative 1,000,000 meters per second? It's like, well, no, it seems like it would violate something, probably violate conservation of energy. So there's probably like some upper limit on what this rebound speed could be. And hey, I bet it would involve like this situation, wouldn't it? Like if you had something that was as bouncy as something could ever be. So this is momentum is conserved. Obviously, that's got to be true. Some of momentum before and after the collision. Okay. But also kinetic energy is conserved. Kinetic energy before the collision, kinetic energy after the collision. Okay. Also equates. Now this is not necessarily true in general, But it is true if you have something that's perfectly bouncy, like this here Newton's cradle, something like that. Or that's pretty close to, pretty close model. Treat this as a system of equations. I know you guys just saw the poster on this, but I'll go ahead and write this out. So you got mass A, velocity A initial, plus mass B, velocity B initial, equals mass A, velocity A final, plus mass B, velocity B final. Okay? That's conservation of momentum. Okay? Then if you do that for kinetic energy, right, that's just one type of energy. 1/2 ma v a naught squared plus 1/2 mb vb naught squared equals 1/2 ma va final squared plus 1/2 mb vb final squared. Right? So that's the same system, right? Just like expanded out. Okay. Right. And okay, so when I took physics back in the day, like high school, college, we were left with this system, and we were given some initial inputs like the masses and some starting velocities, and so like, go, just solve this, right? So if you know the masses and initial velocities of each object, that is enough to solve this system of equations, but it takes a lot of paper and a lot of time. So here is the general solution to that system of equations. The rebound velocity of object A, so velocity A final, where you guys know this final refers to post-collision, because of course we're dealing with collisions here, right, is equal to a big old fraction. Right? So if you go solve this, right, burn lots of paper, lots of time, it's equal to this. Velocity A pre-collision times mass A minus mass B plus 2 times mass B times velocity B initial, say before collision, right, all divided by the sum of the masses. Right? That is the solution every time to that system of equations. Okay? Tell you guys what else too, is that this solution, not in a whole lot of physics textbooks, surprisingly, and also kind of hard to find on the internet. So if any of you guys are ever going to take physics in college, I bet a lot of you guys are, definitely hold on to this page of notes or like print out that poster and hold on to that, because that will save you a lot of paper and a lot of time someday. Okay. So let's solve an example problem with that. Right? So an example. Actually, I want to use the exact same example numbers that I did yesterday in the notes, and we'll see how does it bounce off. It's perfectly bouncy. Okay. Oh, and I call this number 7 because you guys remember this page that I've been referring to sometimes? Okay. Number 7 is a perfectly elastic scenario. So I'm basically going to do that story just with the numbers I used yesterday notes. Okay. So perfectly elastic collision. So we got, let's go, mass A is 3 kilograms, just like before. Mass B is 2 kilograms, just like before. These are headed towards each other, just head-on collision. Everything's just in one dimension. Okay. Velocity A initial, let's call it 10 meters per second, just like yesterday. And velocity B initial, we'll call 15 meters per second, and I'll throw a negative sign on it, just say it's going to the left. Right? Also, just like yesterday, these two are gonna bam, they smack into each other, and then, well, what happens if the two like bounciest bouncy balls in the world bounce off each other? Well, they're gonna rebound. So here's like before, here's after. So mass A, mass B, right? They've already smacked against each other, like bam. Okay. And then what? Well, it's going to be some velocity A post collision and some velocity B post collision. Like that. Right. And just going to take this formula right here and just start plugging in numbers. Just plug in the numbers and see what happens. So velocity object A post collision equals big old fraction. I've got 10 meters per second here times 3 kilograms minus 2 kilograms, difference of masses, plus 2 times mass B was 2 kilograms. All right, times negative 15 meters per second. All divided by the sum of the masses, 3 kilograms plus 2 kilograms. Okay. I'll put this in my calculator all in one go. If you need to chunk this into smaller parts, you can do that too. So you got 10 times 3 minus 2. Okay, so 10 times 1 plus 2 by 2 by negative 15, all divided by 3 plus 2 is 5. Okay, I'm looking at negative 10 meters per second. There you go. That's the rebound speed of object A. Guys, go there. If you're paying real close attention, you might see though that there is one value up there that we actually don't know the value of yet. And what's that? Yeah, VBF. What's the rebound velocity of the other object? Okay. And there's more than one way to get it. What's one way that you could solve for VBF? What's one way to do it? You could.
I mean, would it be the same formula, but like you just swap around like the A's and the B's?
Oh, that's the tricky way. That's the way I was actually going to do. Right? Yeah. Let me write down exactly what Brian said. He said you could just change the definition of what's object A and what's object B. Right? I mean, if this is set up for one of the objects, we could just swap what A and B is. Right? So you could say velocity B final is equal to big old fraction. Well, this would look, well, it's going to run like this. Negative 15 meters per second times 2 minus 3 kilograms plus 2 times 3 kg times 10 meters per second, all divided by 2 plus 3 kilograms. Okay. The other way that you could have solved it is you could have gone back to the general collision formula, just the momentum all adds up. Okay. And then you would have a rebound velocity that was just different from yesterday. Now it's now you know it's this number instead of this number, and then just solve it that way. Okay. Or I guess if you wanted to go through kinetic energy, you could do that too, because that's also conserved. Okay. But you run the numbers on this. This is going to come out to, oh, hold on, I just have my notes here. Oh, there it is. 15 meters per second. Okay. Yeah. Now, I did happen to notice, I think this is coincidental, or there might be something to this. I don't know. I don't think this is universally true. That see how the rebound speeds happen to be the same as the initial speeds? Like 10 bounces off at negative 10 and 15 bounces off at negative 15, or negative 15 to 15. I know that if you change some of these masses, that would not necessarily be true. Like, what if you had, like one of these is like the mass of a whole planet, so it's like moves right, versus a little tiny marble. That these numbers would play a little bit different. So there might be something to this, but not quite sure what the connection is. But
I think I know what it is.
Yeah, what's that?
You have 8 kilograms facing 15, and each has 5 meters per second per kilogram on the other side.
Okay, so these numbers just happen to be nice and work out.
I think it's ratios.
Okay. Okay, so like ratio of 10 to 2 is a 5-to-1 ratio, and 15 to 3 is a 5-to-1 ratio.
Yeah.
Huh. That may be it. It may be something to do with that. Yeah. So. All right. So next here. Okay. So we've got these boundary conditions. You know what perfectly elastic is from the tail end of yesterday. You guys know perfectly inelastic. But what about something in the middle? Like, could you quantify? What if you have like two half-play tennis balls? They're like, and they bounce off each other, but not very well. Okay. how can you quantify bounciness? The physics term for that is called coefficient of restitution. This is a measure of bounciness. Tell you guys what too is that I don't think what I'm going to tell you guys right now is going to show up on AP. What does show up on the AP exam? Maybe like conservation of momentum. Yeah, that could show up perfectly. Inelastic, that's the one they tend to pick. Elastic, know how that works. They're never going to have you guys use that crazy fraction. Do they ever ask you a question about this here? I can't remember ever seeing a question on what I'm about to tell you guys right here, but I want you guys to know this anyway. So coefficient of restitution, like how bouncy is something? Well, this is going to be bounded between two values, but I don't want to tell you right away what those are. I want to tell you what the definition of this is, and then see if you guys can figure these out before I tell you the boundary conditions. So coefficient of restitution is the ratio of post-collision difference in velocities compared to pre-collision difference in velocities. And then I'm also going to throw absolute value bars around this thing because there's a certain intuitive way of putting this together, but it always comes out negative. But here, so how about this? So velocity B final minus velocity A final, these are vector values, okay? All divided by velocity B, say pre-collision, minus velocity A pre-collision. Okay? Now the fact that these objects are bouncing off each other and changing directions, well, you can put in whatever numbers you want. This fraction will always come out to be a negative value. Okay? And there are a couple ways of handling that. One way to do it is this. Well, if it's always negative and you're taking the absolute value, isn't that the same thing as just changing the sign? Right? That's one way to do it. I think what I printed on the poster though is an alternate way to handle it, which is just to like swap two of the velocities. Okay? So you could also do this: velocity B final minus velocity A final over velocity A initial minus velocity B initial. You could also do that. Let's look at a specific story that you could attach to objects bouncing off each other. What if one of the objects is the entire Earth? So that's why I drew a floor here. Okay? I'm going to bounce a ball off the Earth. Okay? So boing. Okay. So there's some V crash and there's some V rebound. Okay? And one reason I like this story as a scenario is because one of the objects, the Earth, is basically not moving. So you can just call it like 0 meters per second. Therefore, the difference in velocities is just the same thing as velocity of the ball, right? Okay, so you can simplify this a little bit. Okay, well, so let's think about last couple days of notes. What are the boundary conditions? Because I want to go back and answer this question, right? What values should you go here and here? Coefficient of restitution is always bounded between what and what. So one extreme scenario could be perfectly inelastic. This ball could be a ball of wet clay. You drop it, it goes, just sticks to the floor. So it had some huge difference of velocity as it was about to hit the floor. But then what would the final difference of velocity be between the ball and the Earth? 0, because it's just flat, right? That would be perfectly inelastic. Wouldn't that be 0 divided by some number? So what number goes right here? 0. You can go down to 0. Okay? And the other extreme situation is you can have the world's bounciest bouncy ball, and you drop it, it goes boing, and if it's the world's bounciest bouncy ball, do you think that the rebound speed could go up to matching the crash speed? Right? If it's perfectly bouncy, that would be the case, wouldn't it? Right? In fact, you'd probably rebound to the same height. Right? So go like boing, 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 just like like thousands of years. You leave this bouncy ball in King Tut's tomb, come back thousands of years later, archaeologists opens the door, whoa, what's that? Boing, 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 right? Do something like that. If there's no energy loss. Right? And if these are the same as each other, then isn't this number and this number the same? So what's the upper boundary on coefficient of restitution? 1. Yeah, 1.0. So then if you had like two half-deflated tennis balls going through, like boing, they bounce off each other but not very well, that might be a coefficient of restitution of like 0.3 or 0.4 or something, right? The bounce balls you guys had last week, maybe it's like 0.9 something, maybe it's 0.95. There is an alternate way of thinking about coefficient of restitution. Using that story that I just showed you guys of bouncing a ball off the floor, right? Based on the rebound height versus drop height. I'm gonna have you guys do this as a lab sometime next couple of weeks. So I'll do capital H for the drop height, and then the ball is gonna go boing and rebound up to probably a height that's not as tall. So I'll use little h for the rebound height. I know this was subscript 2, just to sort of reiterate that idea, right? Drop height and rebound height. Okay. Now, if the rebound height was the drop height, then that would be perfectly elastic. Boing, boing, boing. Right? If rebound height 0, that would be perfectly inelastic. Right? What is coefficient of restitution based on those heights? Right? It probably has something to do with the ratio of those heights, but it's not directly the ratio. But it is related to that. Let's start with the definition of coefficient of restitution. Remember, coefficient of restitution is what is the rebound speed compared to the crash speed. I could do that. I could go V rebound over V crash. Now, since those are opposite directions, I gotta take the opposite value. I'll separate. Okay. What is one of those speeds in terms of the height? Like, what is the crash speed based on that drop height? Hey, you guys have an expression for this. Isn't that the Galileo question? Right? Galileo drops a ball off some tower, how fast it's crashing into the ground? Who remembers the expression for crash speed? Square root 2gh. Yeah, this is one of those things that keeps recurring in this class, doesn't it? Oh, and since this is rebound, I'm going to use little h here, right? And then capital H down here, because the rebound height based on rebound speed, it'd be the same principle, wouldn't it? The square root 2gh just going up. Okay. You guys saw this back in kinematic, back when we were doing kinematic stuff. If you use this third kinematic formula, you get square root 2gh. Right? You guys saw this with conservation of energy, right? And now we're applying this. Oh, what's gonna cancel top and bottom? Yeah, the 2 and the g, right? Ah, take a look at that. It's the square root of rebound height compared to drop height. Right? Now this is an alternate method for coefficient restitution. For a dropped ball. All right, you guys good so far? All right, so let's look at, I've got one more topic I need to cover with you guys here, and that is impulse. Impulse. So impulse is a physics term that just means change in momentum. Change in momentum. Hey, change in, that's like the Greek letter delta, change in. Although every once in a while I use this for like difference in, but usually it means change in. And then P is momentum. So change in momentum. Right? If you ever see delta P. Right? And there's a formula for this. Well, actually, two perspectives on this. Right? Like, how do you change momentum? Right? You might have the thought, well, hold on a minute, I thought momentum was conserved, so how can it change? Remember, momentum is conserved for a closed system, but not necessarily for either an open system or for an individual object that has an external force acting on it. It would involve a force. Let me make some notes down here. So let's think back to Newton's second law of motion. F equals ma. Okay? Put a force on a mass that causes it to accelerate. Okay? You guys have not seen accelerations for quite a while in this class. We haven't been talking about them yesterday or today. We haven't really talked about acceleration over the last couple of weeks. Okay? But you guys have seen velocities all over the place, right? So what relates acceleration back to velocity? Acceleration, what was the original definition of acceleration?
It's like how much it speeds up per second.
Yeah, rate change of velocity, right? So change in velocity per time interval, right? Is that true? And, ooh, mass times change in velocity, just that bit right there. Huh. That's probably what impulse is, right? Because mass times velocity is momentum, so change in momentum, okay, so if I take that time interval and I cross multiply that up, isn't that going to be force times time interval is equal to mass times change in velocity? Okay. That right there is the impulse formula derived from Newton's second law of motion. So go write this up here. So mass times change in velocity is equal to force times time interval. Want to spell this out too. So mass, obviously. Okay. Change in velocity. Right, so some object is speeding up or slowing down. Right? Well, how did it do that? Well, because you applied a force. Oh, I don't want to just say force. I'm going to say average force. Average force. Okay? And there's a reason I'm going to say that. You guys will see. I'm about to make a graph for you guys. Okay? And then delta t is time interval that force acts for. Okay? So if you apply an average force to some time interval, it's going to cause an object of some constant mass to change its velocity by some amount. Okay? Okay, that's impulse. Huh? Guys good? Now, for I want to do an example with you guys, just throw in some numbers, and then do a graph. Right? But before I do that, I do want to give you guys sort of a counterexample to something that I wrote here. Okay? Because if you apply a force for some time interval, sure, that'll change the momentum. Does that necessarily have to go into a change of velocity, though? Right? So here's a counterexample. You could actually change the mass of something instead, and then just adapt this equation a little bit. Okay. Here's maybe something like this. Like, what if you have an assembly line and you have like a belt just moving along, like dropping mass onto it? Wouldn't that be like increasing the mass at some rate, right? Or some falling off the other end? Then maybe it's connected to a motor, or something like that, applying some force to keep going. Okay. Or maybe, actually, here's probably a better example. What if you're pushing a grocery cart down an aisle and you're like throwing a bunch of groceries as you're going along? It's like that you, hey, would you be increasing the mass of your cart as you're pushing stuff into the cart? Like one of every juice bottle, like that one. Okay. Okay. So if you want to maintain, say, a constant velocity, so there was no change in velocity for an increasing mass, you would have to keep applying a force to that to make that happen. Otherwise, the cart would just slow down, right? So sort of a counterexample, though. Okay. But let's run some numbers on this thing. Let's do number example. So we've got this mass times change of velocity is equal to force times time interval. Okay, so what if we have a story of a bat hitting a ball? Maybe I should have written that up here. Okay, so bat hits a ball. Let's use a baseball because mass of a baseball is pretty close to 0.15 kilograms. You guys have seen that number earlier today. Okay. And maybe I'm trying to figure out what is the change in velocity of this baseball if I know the force that's acting on it. So 190 Newton force. And you also have to know how long that force acts for. So guys, what do you think this number, this delta t, this time interval, is probably more realistic? Do you think this should be closer to 10 seconds or a tenth of a second? What makes more sense? Yeah, maybe like a tiny fraction of a second. So I'm just going to copy the numbers from my notes using this many seconds. Oh, I remember where I got these numbers. So on this page right here, if you look at number 10, number 11, are that scenario, you hit a ball with a bat, and there's some questions about that. Number 10 asks the question, what's the change velocity of the ball? Number 11 says, what's the force if you know the change velocity? So both perspectives on this impulse formula. Guess I'm just going to divide both sides by the mass of the ball, 0.15 kg, 0.15 kg. It cancels out here. And then, therefore, the change in velocity of that baseball is, what's 190 times 0.03 seconds divided by 0.15 kilograms? Looking at 38 meters per second. There's your impulse. And then, of course, AP likes proportional type questions. So if you saw like, what if you applied the same force for twice the time? Would the change velocity just be like twice that number?
So you said that's the impulse?
Or I'm sorry, this is I probably said it wrong. Yeah. So this is impulse formula. This is the change in velocity.
Okay.
Yeah. So impulse is mass times change velocity, or force times time interval. Speaking of which, you've got two perspectives on impulse, right? There's kilogram meter per second. There's Newton seconds. That's why if you ever see Newton seconds, it's usually an impulse question, but Newton seconds is the same as the unit for momentum. Now notice what you know and what you don't know. This is a change of velocity. This is not necessarily the final velocity, right? So this could possibly represent, let's say, some possible scenarios, because this could represent a lot of things. Right? Maybe the ball is on a tee. You guys know what a tee is? You have a stick, you put a ball on it, just resting there. A lot of kids use tees to just the balls at rest, you just like, bam, just hit it off the tee. Okay? And if that's the case, wouldn't initial velocity be 0 meters per second? Okay. And if that's true, then what's the final velocity? 38 meters per second. Or maybe you have something like this. Maybe the pitcher throws the ball toward the plate. Let's call it toward the plate in negative direction. At 8 meters per second. That would be negative because it's toward the plate. Right? And let's say all this plays out exactly, like these numbers. Right? What would the final velocity of the ball be headed towards the outfield? 30 meters per second. Right? Or maybe the pitcher threw the ball towards the plate at 19 meters per second. So I'll call it negative 19. How fast is the ball leaving the bat? Yeah, positive 19 meters per second, right? Positive. Right? Guessing the general rule is that your final velocity is equal to your initial velocity plus the change of velocity. Got it right? You guys good? All right, you guys ready for a graph? Ready for a graph? Graph time. All right, so a graph that you will almost certainly see on the AP exam is going to have this set of axes right here. Force in newtons versus time and seconds. Whenever you see a force versus time graph, think something to do with impulse or momentum. You know what? You guys have had this since the very first day of school. You guys remember this page, right, where it summarizes a bunch of stuff? So if you go down to conservation of momentum, right? Oh, hey, look, a bunch of formulas that we've been doing this weekend. Hey, classic example, asteroids slamming against each other. Right? Look at this graph. Force versus time interval. Force versus time interval. Hey, look at that. So let's see what we're going to do with that. Force versus time. Now, this graph might look like a lot of different things, but there is one classic shape that they tend to use, and that's the triangle shape. And I'll show you guys why. I'll attach it to the story of hitting a ball with a bat. You tend to see that right there. Now, this would be like time 0 seconds. Let's use the same example numbers we were just doing. So this would be time 0.03 seconds, and it looks like this would be half of that, so 0.015 seconds. Right? How many seconds that would be? Right? this very first moment is when here's your bat. Here's the ball, and the ball is just making contact with the bat, right? Here comes the baseball, here's the bat. They're just starting to make contact, right there. Okay. Then, flash to this point, here's your bat. Here is the baseball. Getting squashed against the bat. Okay. Bat's still on the move, but the baseball is now changing direction, isn't it? Okay. And then, at this point, the ball is just leaving the bat. So let's draw that one. Here's your bat. Here's the ball. Okay. But now the ball is ready to leave the bat and rebound the other way. Okay. Now that whole process happens in a tiny fraction of a second, but you guys know that. You guys told me that. Right? Okay. Now, how does this pair up with like impulse? Like that whole deal, right? Well, remember how I said that impulse was force times time interval, right? Doesn't this, I mean, if this were exactly translated to a graph, doesn't that look like maybe some height of this graph times some base? Right? That would be like a rectangle shape, wouldn't it? And that's not exactly what I've given you. So maybe you have to expand on this a little bit. What property of this graph do you think represents impulse? An area of that triangle. Right, here's your delta P right here. Okay, so that's the area of that triangle. Okay, where the peak of this triangle is not the average force, it's the maximum force. That's F max right there. Okay. Where do you think F average is? How many of you guys think that average force is exactly half of the maximum force for a triangle? Yeah. Here's your average force, which is exactly F max over 2 if it's a perfect triangle. Okay. Let me tell you guys why. I don't think you guys in calculus have gotten to an average value yet. You guys probably haven't gotten to average value. But when you get to average value, I'll give you guys a story, a model to think about. What if you had a giant block of ice, giant triangle block of ice? You guys see that big old triangle block of ice right there? And we put some aquarium walls right here. So I've got this in an aquarium. Here's a wall, here's a wall. Okay? I'm gonna leave that block of ice there for a few days and it's all gonna melt. Do you think it's gonna probably melt to about that level right there? Yeah, and that would be like a rectangle, wouldn't it? Wouldn't that be average force times time interval? So that's the area of the rectangle, F average times time interval. Okay? So the area of the triangle playing off the maximum force, or the area of the rectangle playing off average force. Okay, either way. Okay. Questions so far? All right, so one more thing I want to do with you guys before you take off is, you guys see this track over here, this like low friction track? Okay. Gonna pause the recording, but we're gonna do a lab pretty soon, so I'm gonna show you guys how this works out.